Hi, this is Guillermo Campitelli, and in this video I continue the case in which we want to investigate the effect of one nominal variable on one numerical variable. In previous video we saw the between subjects design, and in this video I'm starting with the within subjects design. So the case study is the same. Participants were exposed to videos or documentaries, and after 5 minutes of watching the videos they had to rate their happiness level. But the difference is that in this case, instead of having 400 participants, we have 200 participants. But instead of having participants being exposed to just one condition, the participants are exposed to the 4 conditions. So it's called within subjects design because within each subject you can make a comparison between conditions, because the same subject goes through the 4 conditions. Okay, so it's important here to realize that with half of the number of participants we got double of observations, because we've got 200 participants, 4 observations in each participant, 4 measurements of happiness. So we've got 800, and in the previous case we had only 400. So within subject designs are advantageous, because with less participants you've got more data. And there is another advantage of within subject designs. One important confound in between subject designs is that, let's say, even if you randomize samples, so if you randomly assign people to different groups, there's still the groups are formed by different people. So the differences that you find between conditions, in this case in happiness, still can be due to differences between people in other things that are not related to watching the video. So you've got this problem of variability, but whereas within subject designs that disappears, because it's the same person that is in the 4 conditions. So there's no problem there that we've got variability between people. It's the same person. So the question is, if the within subject designs are so advantageous, why we use it? And there is one more advantage. In psychology, most of psychology is about investigating processes within the individual, in their brain, in their minds, however you want to call it, but it's within the individual. So doing within subject design makes much more sense than between subject designs. But between subject designs are more popular. Why? Well, there are disadvantages with the within subject designs, but there are ways of solving those. And the disadvantage has to do with the order effects. So because we have each participant goes through the 4 conditions, maybe there is an effect of the order of exposure. So for example, if it may be the case that when they are watching the 3rd and the 4th film, they got used to the films and they are less stressed, or they get used to the situation, they are less stressed, and that affects their rating of happiness. So basically there is one way of solving this problem, which is counterbalancing. And counterbalancing means to change the order of presentation between participants. So one participant will see poverty first, cooking second, gardening, and then success. Another one will have success first, another one will have cooking first, and so on and so forth. So basically you've got each condition was in the first order, in the first position, second position, third position, fourth position, more or less the same number of times. So you get if that's the case, if there is an order effect, is gonna affect similarly to all the conditions, so it will disappear. Okay, so that's one thing. That also solves the opposite problem. The opposite problem is that people may get, for example, when people have to perform a task, in this case it's just writing, but sometimes they have to perform a task and they get tired, so their performance decreases over time, and that is a problem. But again, if you counterbalance, that decrease in performance will affect all the variables, all the conditions equally. The other one is that you learn how to do the task during the experiment, so the task at the end you get better performance. So these are all sorts of order effects that could appear, but counterbalancing solves the problem. Now, but the main reason that why we use between subjects is historical. We developed our analysis. We borrowed them from other disciplines, agriculture and medicine, and those disciplines are better for between subjects designs, but this is not the case for psychology. So basically, whenever you can use within subjects design, have a lot of advantages over between subjects designs, but they are underutilized in psychology. Okay, so let's continue with the case study. Okay, so let's conduct the descriptive statistics with JASP, and we get the file first. It's in chapter 9, and this is the name: documentary happiness within subjects design, within, and SPSS. And I'm going to explain why it has this name SPSS. Well, the reason why it has that name is because the developer of JASP made a compromise and used this SPSS style way of organizing the data. To me, is not very good, not very nice. It's not very intuitive. I show you this design, documentary happiness within, and I show you why. I want to show you because it makes things easier. So this is the design of the way of organizing the data if you use R. And the beauty of this is that you've got the columns are variables. So here is the number of participants, then the documentary category. So here I use numbers 1, 2, 3, and 4. The order in which it was presented, and then happiness, the score that the participants provided. So you've got here names of variables, and it's very intuitive. Now, what that also implies is that the participant should appear 4 times. So participant 1, 2, 3, 4 until 200, and then it will start again. So we got participant 1 again to 200, and so on and so forth. Okay, so but unfortunately the developer of JASP decided to use the most popular organization of data, which is the one that SPSS uses, and this is this one. So SPSS, like ordering of data, uses one participant per row. So you've got, instead of organizing by column and by variable, it organizes by participant. So you are going to have 200 rows, because you've got one, the participant appears only once in one row. Now, so basically what we have is happiness 1. Forget about order. We've got happiness 1, happiness 2, happiness 3, and happiness 4. So, but these are not variables. See? And this is a combination of the dependent variable happiness with the documentary variable 1, 2, 3, 4, but we don't have the documentary variable in the data. So to me it's confusing, but that's what most researchers in psychology learn, because they typically use SPSS. Myself is not the exception. I learned by using SPSS. So we are used to this, and it's difficult to unlearn. Okay, so that will generate difficulties when in the analysis, but that's the way the developer of JASP decided to do things. So let's do the descriptives. So we go to the descriptives as well, descriptive statistics, and now this changes respect of the between subjects design. So we are going to have the happiness variables. So into variables we are going to have it the happiness scores. So, and that was confusing to me, because these are not variables, these are a hybrid between the name of a variable and the values of the independent variable. Okay, so basically here JASP already, without me telling anything, it did the descriptive table, and we've got happiness 1, happiness 2, happiness 3, happiness 4. Okay, so remember that from now on, happiness 1 will be poverty, happiness 2 will be gardening, happiness 3 will be cooking, and happiness 4 will be success. So the mean of poverty is minus 49.8, the mean for gardening 4.9, for cooking 5.3, and for success 50.5. Okay, so we can ask JASP to generate plots, display box plots, and we've got that. If we like the violin type instead, we just do the violin. Box plot and violin together don't look good, and the jitter shows the actual data. Okay, this time the jitter works better. The superposition of the data with the violin works better. In other cases it doesn't work very well. Okay, and remember, these graphs you can you just press there and you copy and you paste in Word, and it's ready, it's formatted. So we can go to statistics and then tick all the statistics you are interested in. We are going to come back to this for parameter estimation, and we are going to tick the standard error of the mean to get the confidence intervals. Okay, so but we've got here the statistics, and I show you in the slide Here are the statistics, so basically the values that I've already told you with the standard deviations. You can see that standard deviations in poverty and success are much larger than the ones in gardening and cooking. And we've got the violin plot with the data jittered, and the green line shows the mean of each condition. Now, so the difference with the between subjects design is that here we've got 200 participants. These are the same 200 participants and there, same 200 participants and there, same as in the others, instead of having different participants. But the pattern is exactly the same, no changes. And here is a plot of the order effect. So I could have done it with just, but I'll just show you. And just interesting to see that order doesn't have any effect. So you can see that the means are very close to each other. And you can see even in the shape of the distribution, you've got this very unusual concentration on the middle, which is that's typical. This is normal, but you've got this concentration in the tails with nothing in between. So that tells you that that order is not a variable that is good at predicting the values of happiness. So order doesn't have any effect on happiness. Okay, so now let's move to parameter estimation. We start with the traditional frequentist approach, then the Bayesian, then resampling. So for parameter estimation of the means, we just use the standard error of the means in the descriptives, which are those ones, and then we calculate them by hand, the 95% confident by hand. So basically it's the mean minus 1.96 times the standard error of the mean, presented here. And for the lower bound and for the upper bound is the mean plus 1.96 times the standard error of the mean. So I just return to JASP, and I'm going to now tick the standard error of the mean, and it appears in the table standard error of the mean, and those are the values I presented on this slide. Now here we also need to generate a parameter estimation of the differences between the conditions, and we've got two options here. So that's still the means with their confidence intervals, but now we want to estimate the means of the different scores, and there are two ways of doing that. One I'm not going to explain now, I'm going to explain later, which is to obtain the sum of squares of a post hoc analysis in ANOVA. So that's when we use NHST, null hypothesis significance testing. We can do a post hoc analysis to compare the groups. Sorry, to compare the conditions. But I prefer option B, which is a little bit more of work to do, but because I'm always interested in the understanding of things, by doing what I'm going to tell you to do, you will be able to understand the difference between the analysis is done with the within subjects design and the one done with the between subject design. So basically, what I'm proposing to do is to create a new database. So if we look at the data here, you've got all the values for happiness 1, happiness 2, happiness 3, and happiness 4, which corresponds to poverty, gardening, cooking, success. So what you can do is to calculate happiness 1 minus happiness 2. So you create a new column, but actually you can do a new database, and And you've got the different scores between these two conditions. So you've got a new variable called difference between 1 and 2, or difference between poverty and gardening. And basically that variable is a new variable, and you treat it as a new variable. And you can obtain all the statistics of that new variable. And you do that with all the contrasts, the 6 contrasts. So 1 versus 2, 1 versus 3, 1 versus 4, 2 versus 3, 2 versus 4, and 3 versus 4. So you've got 6 new variables, and I've got that in a file, which is documentary happiness within difference. So basically I just have for each participant the different scores in the 6 contrasts. So there are 200 participants, and basically I've got new variables: poverty gardening, poverty cooking, poverty success, gardening cooking, gardening success, and cooking success. So I've got the 6 contrasts as new variables, and now I can do descriptives of just these ones. And so I put all these variables. You can select all at the same time, and you go to statistics, and you get this the mean. You can have more statistics. Standard deviation we use a lot, and the standard error of the mean. So when you see the post-hoc analysis in ANOVA, it will only show you this, the standard error of the mean. It will not show you the standard deviation, because it's tricky, because you are presenting the contrast between two variables. So what that standard deviation means? Well, here we clearly know what it means. It means the standard deviation of this new variable called difference scores between poverty and gardening. So, and the analysis that a JASP and all the software do is based on this. So we never actually get to see that this is done. That's the software is doing this, but this is actually what happens. So I let you do this on your own if you're interested in, but try to do a t-test between these two conditions and see how that compares with the t-test that we are going to do with the raw scores, not the different scores. It should be the same. So basically what the within subjects design does is to generate a new variable and treat these variables as variables on themselves, and then you can do the analysis you typically do with those variables. So here is the table with the mean of the 6 variables of different scores, and standard deviation of that variable, and the standard error of the mean, which we need for calculating the 95% confidence interval. And here are the mean estimate with the interval estimate, so confidence interval for each of the different scores. Okay, so that was the traditional parameter estimation. Now Bayesian parameter estimation. So I use R. JASP we are going to use JASP for the model comparison approach and for the hypothesis testing approach. So it gets unfortunately the web applet that was fantastic that we used for the between subjects design is not available for within subjects design. So we have to do it ourselves with R. So basically we start with a prior that we use for all the mu's, which are the population means for the 4 conditions, and we need to do a very interesting hierarchical model, and this looks very scary, but actually it's not difficult. So I'm going to explain briefly what this whole thing means. So first of all, you've got 3 plates here. The plate I says 1 to 200, plate J 1 to 4, and plate K 1 to 6. So plate I represents the participants. So it means that we've got 200 participants. So whatever is inside the plate I repeats 200 times. So we've got these 2 variables that are within I. So we have 200 H's here and 200 thetas. Now the plate J goes from 1 to 4, and that represents the 4 conditions. So poverty, gardening, cooking, success. So whatever is within the plate J repeats 4 times, like the mu, the tau, the sigma, the pi, and the gamma. They all repeat 4 times. Well, same with K. K is goes 1 to 6, and it represents the difference scores, and we've got 6 contrasts, so that's 1 to 6. So this delta represents the different scores. And the things that are outside plates, they don't repeat. So we've got 1M, 1Z, 1L, 1U. And now theta and H are within I and within J. So basically they repeat 200 times 4 times. So that means 800. And that's what we have. The H is the happiness scores. And as I mentioned before, we've got 800 happiness scores. Theta is our prediction. So the model's prediction of the H scores. And basically what we are saying is that the probability of obtaining each happiness score we use, in order to obtain that probability, a normal distribution with theta as the mean of that distribution, and tau, there's a little bit of complication. We are used to use the standard deviation, but the software we are using to calculate all this it uses a tradition in statistics or a probability theory, which is to use the precision. So tau is the precision. And what's precision? Well, it's the inverse of the dispersion. So dispersion tells a large dispersion value means that the distribution is very very flat. The precision, if you got a high precision, then the values are all very close to each other. If you have a low precision, the values are dispersed. So it's the opposite. So basically, here we calculate the tau with the sigma. Actually, the actual calculation is tau equals 1 divided by the square of sigma, or the variance. So this is just technical, and the reason why this variable has a double contour is because it's determined by this one. So we don't have to estimate this value, it is determined by this one. Okay, so basically for determining the probability of obtaining each possible happiness score, we use a normal distribution with theta as a mean and tau as precision, and we don't use a prior to tau, we use a prior to sigma, which we understand a bit better. So now we use as a prior a uniform distribution with the lower value 0, the upper value 100. So basically this is like an informative prior, meaning that all possible values of sigma are allowed. Okay, so this theta is comes again from a normal distribution, and that's why it's a hierarchical model, because we don't just have a prior for theta. We've got theta comes from another variable, and that variable has a prior. Okay, so thetas are the predictions for each individual. So that's why we have 800 for each individual in each condition. So that's why we've got 800 thetas. Now, we've got an enormous amount of possible values of theta, same as h. And so, how do we calculate the theta? Well, the theta comes from a normal distribution. And that normal distribution, the mean is mu, but it's the mean of each condition. So we've got only one mean. So these are 800 thetas, which are our predictions, and these come from a normal distribution in which they use 4 means, one for each category. And this is again a precision, but at the different level. So that gamma is the precision of the normal distribution, and as we did with tau, this is calculated and completely determined by that's the standard deviation of the normal distribution, pi, and this comes from a uniform. The prior for pi is a uniform with lower value 0, upper value 100. And so the mu's are very important for us. Even though we are going to estimate these 800 thetas, what we are more interested is in the mu, which is our estimation of the population means of each condition. And this one has a prior, and that's the one I showed you with a and here I'm defining the prior as a prior with a very low precision. So a normal distribution with mean 0 and very low precision. Being the precision very low means that it's very flat. So again, it's an uninformative prior, and I'm going to go back. I'm going to back. It's actually this prior. So each of the mu's is this prior. So basically, values very close to 0 for each possible. But the important thing here is that they all have the same plausibility. Values from minus 100 to 100. And finally, we can completely, when we estimate the mu's, we just do mu of j, the mu of poverty minus mu of gardening, and we'll repeat that for the 6 contracts, and we've got it here. So the most important of the parameters is the mu. This is the prior, and we use this model to calculate the posterior. Okay, so this is the posterior. We run a software that is called JAX, and it calculates, it does Monte Carlo, Markov chain Monte Carlo simulations, and it produces a posterior distribution for each mu. And here I show you for mu1, which is the one for poverty, is here. It's very around. So here is the mean of that distribution, minus 49.8, and you can see that the intervals are very small, So that's you can see here. For mu2 gardening and mu3 cooking, they are close, so close that you can't see them, and they are, remember that their standard distribution was very small, so that is reflected here. The interval is even narrower than that one, so that's why you've got a spike also almost there, and much more than this one. You cannot see visually, but this one is much more concentrated around the mean than this distribution, and same as this one. This is the distribution for success, the posterior distribution with the mean of 50 and confidence interval 49.4 to 51.6. And also we've got the deltas. The deltas are the mean differences, and we've got here the posterior distribution with means and confidence intervals. And here we've got, for example, this one is poverty minus gardening. This one is a poverty minus success. This one is gardening minus cooking. You can see that is zero, is around zero, because they are very close to each other. And so basically the poverty minus gardening and poverty minus and poverty minus cooking, they are, you cannot see the difference because cooking and gardening are so close to each other that that whatever you subtract from them would be the same. And the same applies to cooking minus success and gardening minus success. So basically they are here. They are together because gardening and cooking are so similar that when you subtract success, it will be the same result. Okay, so that's parameter estimation using Bayesian parameter estimation. Now, last thing is resampling, and I did it with R. Basically, from the samples of the 200 scores for poverty, 200 scores for cooking, 200 scores for gardening, and 200 scores for success, you generate new samples by resampling. I explained that in previous videos before. So basically, with these new samples for each of the 4 conditions, you've got, let's say, 5,000 new samples. You calculate the mean of each sample, and then you calculate the mean differences. So basically you've got 5,000 means for each condition and 5,000 means for each contrast. So here I'm showing you, well, these are the estimation of the contrasts by resampling, and here as an example I show you the difference between cooking and success.